All right, so our next speaker is Heike Rauer. Oh wait, no. So Heike could not make it, so Annelies Mortier is going to talk to us about Plato.
Yeah, so hi, I have no beef in the Super Bowl. The goddesses and the gods of the Plato mission couldn't be here, so I was tasked to talk to you about Plato, so I'm going to do my very best to channel my inner Plato goddess. All right, so the Plato satellite, if you haven't heard of it, is the next M-class mission from ESA, which is the European equivalent of NASA. And it stands for, this is not that contorted of an acronym, it stands for Planetary Transits and Oscillations of stars. So the launch is in the last quarter of 2026, and we're going to L2, so Roman will race you there. We'll see who gets there first. Plato is basically a multi-telescope machine, so we'll have 26 telescopes on board, and it is designed to do high-precision photometry. Now, for bright stars. I'm very biased towards bright stars, so that makes me really happy. So what do we mean with high precision photometry? It is basically 50 parts per million over an hour for any star brighter than V magnitude of 11. I know, wow. So basically, it's quite a machine. So the field of view is about 2 billion pixels, which is 200 times the size of Kepler. So again, wow. And the size is, well, this is really large and really heavy, and we're going to shoot it up in space regardless, obviously. Well, look at the size. It's probably smaller than JWST, though. Okay, the methods, we're doing high precision photometry, so obviously this is about transits and astroseismology, both concepts that you know already. So the Plato mission is really a mission to detect and characterize the exoplanets and characterize their host stars. It's been biased towards Earth twins. I'm biased towards Earth twins, which must be why they asked me to talk about this. So it is really optimized to find these Earth-like planets in habitable zones around solar-like stars, and at the same time characterize that solar-like star. So we're going to do transit photometry, giving you all kinds of sizes of your planets that you're after, inclinations, orbits, periods, etc. It's going to do astroseismology, basically giving you stellar masses, radii, and ages, and it's especially that ages thing that is really impressive, of course. And there's a ground-based segment to our space-based mission where we're actually also going after the radial velocities of the prime sample of exoplanets and actually getting also the mass of our exoplanets. So what that means in total is that we will have both planet bulk densities, as well as stellar densities, obviously, and you'll have at the same time very precise stellar and thus actually planet ages. So you'll have very precise densities and ages of your family of planets. All right, so obviously it's not just about collecting data. We want to answer some science questions about this. And one of the main science questions that drives Plato is, how do planets and planetary systems evolve? How do they form and how do they evolve? And that's where that whole age thing comes into play, because you will get the planets over time. Now, the other question to answer is our solar system unique, or are there plenty of other solar systems out there? Now, I haven't actually quite made my mind up which one I would like best, but both are actually super exciting, and we will be able to actually answer that question. Then, of course, habitability. If you're going to trace and if you're going to be sensitive to the habitable zone, you will be able to answer questions with respect to potential habitable planets. And then, obviously, it's someone else's job to go and find biosignatures on these things. Now, because we're doing planet bulk densities, we will also be answering questions: what are planets actually made of? And perhaps finally answering that question, these freaking sub-Neptunes, what are they actually made of? And last, but definitely not least, is also about the properties of stars. Properties of host stars is what it says here, but really, it's going to be about the properties of all stars in the Plato field. Well, sort of. So the objections, The objectives, as I said, so it's basically about everything to do with your planets. It's about their architecture, their formation, their evolution, and how it correlates with stellar parameters, because we will have very precise stellar parameters as well. It's going to be about the masses and the radii and the ages that you directly get from the astroseismology, but if you're going to follow up with radial velocity your prime sample, you get a ton of stellar spectra as well of that prime sample of stars. Obviously, with any good space mission that does transit photometry, you will be able to select the best targets for atmospheric follow-up, and then some of you can go and play with that and get the actual good atmospheres on these things. At the end of the day, it is about planet evolution over time. We will be able to have planets with very precise ages, and you will literally see the evolution, here's the hope, you will literally see the evolution of planets with time. Now, so internal structure of stars, as I said before, and then a whole bunch of other things that you obviously can also do because you collect a ton of data. Now, what is actually required in order to do what we want to do with this is the accuracies that we need on our planetary and our stellar parameters are actually quite impressive. So for radii, we need about 3 to 5%. That is the goal. Now, challenging, obviously. Doable, probably. Then for masses, we're going for a 10% mass precision. Challenging, very, but a good thing is that the EPRV community likes a good challenge. And then for ages, stellar ages, and thus planet ages, we're also going for 10%. Again, challenging, very, but I think our astroseismic heroes also like a good challenge. Now, all of this, it would be for a bright G-dwarf star, basically the sun. So, just to put this in perspective. On the left, what you see here, so there's one blatant mistake on this paper, on this slide. It says Heike Rauer et al. Submitted, and I was told this morning that the paper got accepted this morning. So yay. Now, I have very little to do with this. So as you can see here, so this is stellar mass versus semi-major axis, and that green thing is our habitable zone. Now, and this is for all planets smaller than 10 Earth radii and less massive than 15 Earth masses. Where, very confusingly, the color is size and the size is mass of the planet. But yeah, stick with it, that we currently have found. Now, if you then look on the right, that is the same population with the required precision and accuracy that we want from Plato. So currently, those are the only ones with 10% mass and 5% radius accuracies. So when I say challenging, I mean challenging. So Plato is going to do it the inappropriately large scale of Plato. So it is going to cover that habitable zone and trying to fill in that gap to precisions that we currently actually are not reaching. When it comes to the stars, because the O in Plato stands for oscillations of stars, it's also going to be wildly exciting. So it's going to be wildly exciting for giant stars, but if you forget about those for a moment, I apologize to astroseismic giant fans, but this is basically luminosity versus effective temperature in log scale and flipped because we're astronomers. So this is basically the main sequence and the subgiant population that you see of stars. In the dark blue are the ones where you will have a confident astroseismic detection after 30 days on the left and after the full 2 years on the right. As you can see, even after 30 days, it is almost all subgiants with good astroseismic detections and a good bunch of the actual main sequence dwarf stars. After 2 years, most of the G-dwarfs and a considerable amount of K-dwarfs will also have astroseismic detections. And I very much apologize to M-dwarfs, but they're not faint and they're not bright anyway. So, So the instrument of Plato, as I said, will have 26 cameras. So it is 24 normal cameras, whatever that means. So there are 12 centimeter cameras, and then with a 25-second readout time. But then we'll have 2 fast cameras as well that will look at the very, very brightest and with 10 times as fast readout, hence why it's called a fast camera. Now, so it's operating in the optical, and then you can see a mosaic there of what the field of view actually looks like. So not every star in the field of view will be seen by all 24 cameras. So the middle will be probed by all 24, and the sides will really only be probed by 6 cameras, but still you have quite a large field of view. Now, the target fields, I know you're excited about knowing where we're going to point this thing because we value equality. Why wouldn't you? We're both going to look in the southern hemisphere as well as in the northern hemisphere, each for 2 years each. So we're going to stare for 2 years in the south, and then we're going to stare for 2 years in the north, and then we're going to hope that we can do a mission extension for a couple years as well, because we'll have consumables for about 8.5 years in total. Now, as you can see on that plot there, so the blue flower is Plato, and the little pinkish thing, that is basically Kepler, just to show the size difference. But both the currently selected fields for the south, as in the north, also somewhat overlap with the TESS continuous viewing zone. So for the stars that we're targeting, several of those already have long-term high-precision photometry already. All right, complementary science, as I said, there's a ton of other things that you can do with this because a photometric space mission doesn't discriminate, and it's not just about solar systems and habitable zone planets. You're basically looking at all the stars, so you will be able to do any kind of close-in giant planets as well, circumbinary planets, young stars, planets around evolved stars, you name it. And 8% is for you guys, is the guest observer program. Well, 8% of the time will go to that. And with my 10 seconds left, I will tell you that we are very much on schedule. The cameras are being delivered on time, tests are being done currently, and we signed the contract, I say we in a very general sense, we signed a contract with Arianespace, I think 2 weeks ago or 3 weeks ago, and we're launching with Ariane 6 at the end of October, and this is the entire Plato consortium. Thank you.
All right, so there's a question way in the back.
I will do my very bestest to answer questions.
That was an excellent overview. Can you speak a little bit about the release plans for planet candidates from Plato, and if those are going to be published publicly and on what kind of cadence? And then maybe also what the RV follow-up looks like, because that's my favorite part.
So the release plans, it's not like, to my knowledge, and I apologize to all the Plato goddesses if I'm wrong, so it's not going to be like Roman, and it's not going to be public immediately, so it will be on a rolling basis. As for the follow-up, currently we're looking at the proposal-based, so lots of proposals going to the ESO telescopes, HARPS, Espresso, and then in the north, HARPS North, HARPS 3. And then for the slightly larger candidates, you can do things like SOFI, but currently the plans are, we're getting organized to put in very focused proposals with the community, essentially. Gosh, that's a lot.
To the right, it was.
Hi, thanks very much, James Rogers, Cambridge. Are there any plans to target young stellar clusters?
Yes, so the northern field that has multiple young stellar clusters embedded in it. It was one of the motivating drivers, so I encourage you to go to, so Valerio Nascimbeni has a paper that came out a couple weeks ago that describes it, but definitely the northern field has multiple young stellar clusters embedded in it, yeah.
Casper?
You were mentioning the requirements for the precision to do the science target. How are you going to deal with the confusion in terms of the pixel size? Do you have any direct plans for that?
I will not deal with that at all, and I don't know, is the honest answer.
All right, and there's an online question, Catherine?
Yes.
They said, this is very exciting. How can we get involved?
In order to get involved, I encourage you to check the ESA website, the Plato mission. The Plato mission consortium is relatively open right now. You do have to sign an NDA, but obviously. So I encourage you just simply send an email and then follow the instructions that follow.
All right, what's that? Let's thank Annalise. Thank you.